Okay, so here's the last section of our review chapter. It's on exponential and logarithmic functions. I'm going to start by just reminding you what an exponential function is and what it means to be the base of an exponential function. Then I'm going to remind you what the exponential constant e is, give you a characterization of it. Then we'll talk about logarithmic functions and their properties. Okay, so we'll start with exponential functions. And in order to define an exponential function, you need to start with a positive number to use as its base. So we're going to start by saying let a be a positive real number. And it's to be understood in this context that a is constant. So I didn't write that down, but I'm going to say it. So a is a constant fixed number. So now you can define the function f in the following way. It takes as input some number x, and then it just simply raises this constant a that we just mentioned to the power of x, and then returns the result. So that's what it means to define a function with this rule, and that's called the exponential function with base a. So let's add that in. And like any function has a domain. In this case, the domain's all real numbers. So exponential functions are defined absolutely everywhere. And let's talk about their graphs now. So there's actually three different pictures that you might see for the graph of an exponential function, technically, right? It depends on the value of this base a. So the first case that we'll sketch, so case 1, is when a is greater than 1, right? That's one of the possibilities. If a is greater than 0, there's three possibilities, really. A could be greater than 1, could be equal to 1, or could be less than 1. So we'll deal with each of those cases. So if a is greater than 1, this is what the graph is going to look like. It's going to cross the y-axis right at the point y equals 1. So it's going to go through the y-axis at 1, and what's going to happen is it's going to grow as the values of x move to the right, and then as the values of x move to the left, the graph is going to get closer and closer to the x-axis. It's going to get, in fact, arbitrarily close to the x-axis, and the x-axis is actually a horizontal asymptote of this graph. So as you move to the left, these values just get closer and closer and closer, almost like a plane that never quite lands, right? They get closer and closer to the x-axis but never quite touch it. Okay, that's the picture you'll see for the graph of an exponential function with a base a that's greater than 1. What about the case where a is equal to 1? Okay, so that may seem a bit weird because look what happens. Let me sneak a note in over here. What happens if a is equal to 1? So if a is equal to 1, then what does this function look like? Well, we still would have f of x is equal to ax. If you want a to the x, if you want to talk about the exponential function with base a. But if a is equal to 1, then this is really just 1 to the power of x. But 1 to the power of anything is 1. So really, you just have f of x is equal to 1 for every real number x. So if a function outputs 1 for every single value x in its domain, which is the real numbers, then really it's a constant function. So in this case, f is constant. So really, what do you have? That means you just have a flat line, right? In fact, you could almost argue that this isn't really even an exponential function. But technically it is, since the definition allows for the case where a is equal to 1, because that's certainly a number that's greater than 1. But this isn't really what we mean when we say an exponential function. If I show you a graph of this function, I ask you what type of function is here, you're probably going to say it's a constant function, it's a flat line, and that's a much better answer. Is it still technically an exponential function? Yeah, okay, but it's not a very interesting case of an exponential function. So we're not going to put really any weight on this case. When we talk about exponential functions, we're only going to care about the case where the base is greater than 1, or in case 3, which we haven't drawn yet, a is less than 1. But no, you still have a is greater than 0. So the case should actually be that a is strictly between 0 and 1 because we still have a positive number a. Okay, what happens in this case? Well, you get the same picture as what we had over here in a sense, but it's just reversed, so to speak. It's flipped across the y-axis. It's still going to go through the point 1 on the y-axis, but this time it grows in the other direction. As the values of x move to the left, the y values of the points on the graph go up arbitrarily high. So it grows without bound in the vertical direction. And then as the values of x move to the right, the graph of the function gets arbitrarily close to the x-axis, you really have a horizontal asymptote again, but just in the other direction. I think I'll make this worse or better, I'm not sure. I think that's about as, if I add any more, I think I'll just ruin the picture. But that's the graph that you would get in the case where a is less than 1. So that's what the graph looks like. Now I want to mention for the moment that all these graphs, for any choice of a, you can sketch something called a tangent line at the particular point where the curve crosses the y-axis. And I'm not going to add them to these pictures up here. In fact, I'm just going to show you the ones down here, and there's already some lines drawn for us. That's actually why this is the one section I did print this page in color. I'm not going to do it all the time, but I did. It's actually for this. These pictures are the reason that I printed these particular ones in color. Let's read this carefully. When a is not equal to 1, so in other words, forget about this middle case. We don't really care about this case. Consider the slope of the tangent line to the graph of, here's the equation that represents the exponential function, to the graph of the exponential function at the point 0, 1. Remember, they all go through the y-axis at the point 1. So that's what we mean by the point 0, 1. We're talking about this point here. So in general, the slope of that tangent line is going to depend on the base a of the exponential function. By the way, when I say tangent line, I mean the line that touches the curve at a single point. Most of you, if you've taken math in high school, at some point you would have talked about an introduction to geometry. We talk about angles, lines, parallel lines, perpendicular lines, circles, and then at some point you'll define a tangent line. And a tangent line to a circle is a line that touches the circle at exactly 1 point. Just generalize that idea to any curve. There's no reason it has to be a circle what you're talking about. You can talk about the tangent line to a curve. It's just it's a line that touches a curve at a single point. Let's actually draw the point in each of these pictures. So here you've got a tangent line to this exponential curve. I'll come back to this other stuff in a moment, but you can see that it touches the curve at exactly 1 point, right at the point where the curve crosses the y-axis, but at no other point. Here, and then this one is going to happen here, and then this one is going to also happen at that same point. Okay, so that's what I'm drawing here. Now, so what are we talking about? So each of these pictures contains a line, and each of those lines has a slope, which we're labeling as m. But each of the pictures also has an exponential curve, or in other words, the graph of an exponential function, and they each have different bases. So let's look at the first two at the moment. So this one has base 2. So if I want to write out the equation of this exponential curve, I'd really have y equals 2 to the x, right? Because it's y equals a to the x, but in the case where a is equal to 2. So that's what this curve is. And what is being given to us, let me be absolutely clear here. We didn't calculate that m is approximately 0.7. It can be done using some techniques, but we don't have them yet. So for now, take my word for it that the slope of this tangent line is approximately 0.7. That's what's being given to us in this example. And by the way, I haven't used this notation yet. You see those two squiggly lines? It looks like an equal sign, but with the two lines are curved instead. That's just stands for is approximately equal to. So this just says that the slope of the tangent line in this picture is approximately 0.7. So you could write the equation for the tangent line as follows. I could write y is equal to 0.7x plus 1. What am I doing? I'm really just writing y equals mx plus b, where instead of the slope m, I'm putting the actual approximation for the slope, which is 0.7. And then instead of the b, I'm putting the y-intercept, because remember, these graphs all hit the y-axis at the point y equals 1. So you know that if that's the point where the tangent line touches the curve, then you know that the line goes through the y-axis at the point 1, and that's why I can put a 1 here. Okay, so here's the equation of the exponential curve, and here's the equation of the tangent line. Let's just do that for the other one as well. So what's happening over here? Well, here we've got an exponential base of 4, so that means this exponential curve is really y equals 4 to the x. And how is that going to affect things? Well, what ends up happening is the larger your base is, for values of the base that are greater than 1 in particular, the larger the base, the faster this curve is going to grow. So in other words, the less far you need to go away from the y-axis before this curve gets very large. And what that has an additional effect of is making this tangent line get steeper. So you can see in this case now the slope is higher, right? The slope, it was 0.7 before, but now the slope is pardon me, I got this sideways. The slope is 1.1. So this one has a steeper slope than this tangent line. So but if I want to write the tangent line, let's do it again. So I'm going to have y equals 1.1x plus 1, with the understanding that these equations are approximately the equations of the tangent line. They're not going to be exact because the slopes were approximate. Okay, so these two examples lead into really what the main point of this third one is. Okay, so for the moment, notice that this tangent line had a slope of 0.7, which is less than 1. And this tangent line had a slope of 1.1, which is greater than 1. It might be hard to figure out exactly how to make it happen, but you're probably willing to believe at this point that there's some value of a, probably between 2 and 4, somewhere in the middle, somewhere in between, that we can choose just the perfect exponential base to make this slope not less than 1 and not greater than 1, but actually exactly equal to 1. Okay, and I'm not saying it's easy to find that number, but I'm hoping that you're willing to accept that there is some number out there that would make it happen, and that's the point of this. That's actually what the exponential constant e does. It's the unique number that makes this exponential curve just grow fast enough, just steep enough, so that the tangent line here at the point y equals 1, this tangent line has a slope of exactly 1. That's actually what the exponential constant e is. So let me just emphasize that now. This is called the exponential constant. So e is the exponential constant. That's really a term worth underlining. It's a very special number. It's irrational, very much like the number pi is. It serves a very, very specific purpose, and it's a very powerful number to have, but it's irrational. And really, we don't know it exactly. Nobody really can say what it is exactly. We just know that it exists abstractly, and we can approximate it with several decimal places of accuracy if it ends up being advantageous to do so. So let me just add that in. By the way, the exponential constant e, you can approximate it by 2.718 if you like. There's no obligation to do that. You can just work with it as an abstract symbol, just like we work with pi and the square root of 2 as abstract symbols. But just like you can approximate pi with a few digits when it's useful to do so, you can do that with the exponential constant e as well. So in this case, our curve would be y is equal to e to the x, and it has the property that the tangent line going through the point y equals 1 on the y-axis has slope exactly 1. So in this case, this is the only case where the tangent line equation is exact. So I'm writing y equals mx plus b, where m is equal to 1 in this case. So I just write y equals x plus 1. So that's actually the way you define the exponential constant. It's the base that you would have to choose in order to make it just grow steeply enough that the tangent line has a slope of exactly 1. And it turns out that there is such a number that exists and will make that happen, and you can approximate it using this approximation if you like. And it's called the exponential constant. By the way, this function here, the exponential function with base e, is called the natural exponential function. So that's actually worth highlighting as well. Since we're here, let me put a circle around this. That's another piece of terminology. So y equals e to the x is the natural exponential function. So let's add that in. Okay, and that's really all I want to say about exponential functions, except for a few properties that we'll add in at the end of this page. But that's basically your review of exponential functions and what they are and what they're good for. We'll encounter them in this course plenty. Here's some laws and or you can call them properties, whatever you like. And we're going to start with a couple of numbers a and b. We're going to assume that they're both positive. Really, what we want is for them to be suitable choices for bases of exponential functions. And then we're going to also need two more numbers, x and y, and they're allowed to be absolutely any real numbers at all. So these are going to be typical numbers that you might plug in to an exponential function with either base a or base b. Okay, so here are the laws. Some of these are familiar from other settings, and they all should be somewhat familiar anyway, but here they are. The first one says that if I take a and I raise it to a power, and if that power is formed by adding x and y together, well then that's what this notation means, right? Add x and y and then put it as an exponent on the number a. It turns out there's another way to compute this, which often will be more straightforward. Turns out you can take a, raise it to the power of x, and you can take a and raise it to the power of y, and you can compute both of those powers separately and then multiply them, and that will give you the same result. So that's the first law. The second law says that you have a similar result for subtraction. If I take a and I raise it to the difference of x minus y, well, it turns out you can evaluate that by computing a to the x and a to the y separately also. But instead of multiplying them like you do in the first law, you're going to actually divide them. So you would take a to the x and you'd divide it by a to the y. So a to the x minus y is equal to a to the x divided by a to the y. The third property tells you how to handle nested exponents. So if I were to take a and raise it to the power of x, for example, and then take that entire calculation, so finish that calculation, completely work it out, and then take the result and raise it to the power of y. That's what this notation means, right? First raise a to the power of x, then whatever the result is, raise that to the power of y. It turns out you can evaluate this by just doing a single power, where your exponent is actually the product of these two powers, x and y. So you take x and y, multiply them first, and then raise a to that power. That's the third property. And that law says that you can do that. So that's how you handle nested exponents. The fourth law tells you what to do if you have two different bases, a and b. This is where b is going to come in. If you multiply a and b, and then you raise the product to the power of x. So you have a single exponent, but the base of this power is a product of two factors. It turns out you can raise each factor to the power of x separately and then multiply the powers afterwards. So that's what the fourth property says. Okay, so that basically covers exponential functions, and then on the next page we'll tackle logarithmic functions.